back to what we were talking about yesterday. We want to move from average rate of change to instantaneous rate of change. And we said that the slope of a tangent line can be interpreted as a rate of change. A secant line could be interpreted as an average rate of change. The slope of a tangent line can be interpreted as an instantaneous rate of change. And that interpretation of rate of change is really important for us. It's really useful for us. And so we're going to be able to use limits to move from average rate of change to instantaneous rate of change. So I'd like to do one example here, and then I'm going to give you some time to work some examples out of the textbook. What we want to do here is we want to find the slope of the curve f of x equals x squared at the point 1, 1. So we want to know what is the slope of the tangent line at this point. So we can get a picture of what it's going to look like. You can graph it kind of crudely by hand if you want a visual, but you don't really need it because we're going to do everything algebraically. But the x squared curve looks like this. The point 1, 1 might be right about there, so we want to know what the slope of that line right there is. That's our goal. Find the slope of that line. You can see from the picture that it's going to be positive. You can see from the picture that it's probably going to be greater than 1. Although I drew it by hand, I don't know how accurate it is, so I wouldn't trust it too much. But you can get an idea of what our answer should be from a picture like that. So what are we going to do? We're going to use that difference quotient. So the difference quotient gives us a slope. I'm going to write it without the limit first, which means that it would be the slope of a secant line, and then we'll throw the limit in there to make it a tangent line. So the difference quotient looks like this: f of x plus h minus f of x all over h. I'm sorry. Those x's should be a's. I'm getting a little ahead of myself here. All right, so what this gives us is the slope of a secant line where the left endpoint is going to be at x equals a. The right endpoint is going to be a distance of h from a, okay, along the x-axis. So what do you think our a value is going to be for this particular problem? Yeah, we're going to take this x value right here and plug that in for a. Okay? I could work with that, work with this difference quotient here, put 1 in for this particular function. I can simplify it and get the slope of a secant line for any interval width that I want. But rather than do all of that and then apply the limit, let's go ahead and apply the limit right away. So if we want the slope of a tangent line, h is going to get close to what? H is going to get close to 0. So we're going to take the limit of this as h approaches 0. All right, so this is just going to be some algebraic substitution. The first thing here, the first term, is f of a plus h. So how am I going to introduce that into the problem? So first of all, a is going to be 1. I'll just throw that in here right now. But if I want to know what f of 1 plus h is, I have to use the x squared function, because that's f of x. So I'm going to put the 1 plus h in for x squared. So we're going to, and don't forget the limit, we're going to compute the limit as h approaches 0 of 1 plus h squared minus, what's f of 1 going to be? 1. You could either get that from the function, or I actually gave it to you by giving you this point, right? So either way works. So minus 1 over h. Okay? Now, if I try direct substitution here, just put a 0 in for h, what's going to happen? We get 1 squared minus 1 is 0 divided by 0. So direct substitution doesn't work, which means that I have to try to manipulate it algebraically. And when I'm doing that manipulation, I can remember, and I can use the fact that h is not equal to 0, because we're taking the limit as h approaches 0. All right, so if I simplify the top, the 1, well, I need to expand it. I'm not going to skip steps here. So we're going to have 1 plus 2h plus h squared there, right? The ones are going to cancel out. So this is going to equal the limit as h approaches 0 of 2h plus h squared over h. Still, if I try direct substitution, I would have 0 plus 0 divided by 0, still 0 over 0. Can't do it still. But what can I do? Yeah, I can divide top and bottom by h. A lot of people have different ways of showing this, but essentially what we're going to do is we're going to factor an h out of the top and then cancel it with the h in the bottom. And when we do that, we're going to have an h cancel here, here, and one of these here. And so we get the limit as h approaches 0 of 2 plus h. Now it's important to understand that the reason this works, the reason we're allowed to do this and not worry about domain, is because h is not equal to 0. It's approaching 0. Can I use direct substitution now? Yes. Yeah. Take 0, plug it in for h, and what do you get? 2. So what we just did is we found the slope of the tangent line at the point 1, 1 for the curve x squared. And we had to use this idea of limit. Now, I told you we're not going to formally define limits in this class, but intuitively you can kind of understand that what we're looking at here is when h approaches some value, and the key to that is we're approaching it. I'm going to say that a lot, especially early on. We're approaching 0, so h is not equal to 0. And that allows us to do some algebraic manipulation that we weren't allowed to do before. Or at least we would have to tag on some domain restrictions before. Now we don't have to worry about it because we know h isn't in the domain. Well, it doesn't need to be in the domain because we're not even looking at what's happening there.